This is section 11.2 series, and this is the example 2 that we've been working on, which I'll scroll up here. Oh, actually example 3. Determine whether the series is convergent or divergent. If it is convergent, find its sum. So on part C, we got the series of 3n to the minus 1, that quantity minus 1 over 6 to the n minus 1. So just kind of throwing something out there, we had just talked about the divergence test, so if you were to take a look at that, what that involves is taking the limit of the general term 3n minus 1, that quantity minus 1 over 6 to the n minus 1, and seeing if you get a non-zero value for that. If so, it's divergent. So looking at this, we have infinity over infinity, which we could use our friend L'Hopital to do, and this is actually not going to be too bad doing it this way. Other ways to do with algebra, derivative is natural log of 3 to the n minus 1. Technically we're doing the chain rule here, but the derivative with respect to n of the inner function n minus 1 is just 1. So I could be a little bit lazy there. And then we have ln 6 to the n minus 1 by similar reasoning. And so then note here, we can write this together. Actually, let me put my constants out front first. ln 3, ln 6 is a constant, and we got times 3, 6 to the n minus 1. And so looking at this, because 3, 6 or 1/2 is less than 1, and then I guess technically bounded by -1 and 1, then we can say this limit is 0 times the constant, which is 0. So I'll just put some notes here about that with that justification. Was an 11.1 with a little rule that we had the limit n goes to infinity r to the n equals 0 if r is bounded by 1 and -1. Okay, so going back to the divergence test, we got 0 for the limit. So what this means is we can't tell anything with the divergence test about whether it's convergent or divergent. So in the divergence test, can't tell anything. About the convergence or divergence when the limit of the general term is 0. So we just stop and we need to take a new approach. Okay. So one thing you might have noticed is that it's geometric-like in that we got a power that's a value as its base, and then a n minus 1 as its exponent, or just anything with n in it might be suspect. So the geometric series on your formula sheet here is of the form a times r to the n minus 1, and so we want to get in that form so we can identify the a and the r and kind of work that out. So we had one kind of similar to this in that we had multiple things to the power of n, and then we try to put them together was the strategy. So kind of a similar thing here. But this one ends up being 2 terms. I'm going to split this up into 3 to the n minus 1 over 6 to the n minus 1, and then we're going to have minus 1 over 6 to the n minus 1. Okay, So each of these things can be written actually as separate geometric series. So let's do that. We're going to have 3, 6 to the n minus 1 minus 1 6 to the n minus 1. And then we can simplify a bit here. 1/2 to the n minus 1, and then we'll have minus. We'll break up this series. 1 6 to the n minus 1. Now technically in hindsight, when we look at these, we can only split up the sum, the infinite sum, if each of these are convergent. So, but like a lot of the limit rules, you can't tell until you actually try it. So just a reminder. So looking at this, let's characterize these. I guess I could take it a step further. We can tell here if they're convergent or divergent, but just to write this out here, that we have the power of n minus 1, so our a is 1 here, just to kind of put that in there. Okay. And so now we have a geometric series. We have a equals 1, and we have our r is equal to 1/2. For the first one, we have a equals 1 in the second one, and we have r equal to 1 6. So the little thing that you do up here tells you to take the absolute value. And then if that absolute value is less than 1, it's convergent, which is what we got going on with both these. So that's good news. If convergence is good news, I guess. Not to be partial to that. Anyway, each of these are convergent, which means we can write them as a sum here. So you see we got this little formula in here. And so we can take this a step further and write them down with the a, with this thing, as 1 over 1 minus 1/2. And this is minus 1 over 1 minus 1 6. Start writing over here. So we're going to have 2 minus 1 over 5/6, 2 minus 6/5, and you do the work there and you get 4/5. So now in hindsight we can say each of these series were convergent geometric series, and we were totally fine in the step where we did the subtraction of the two terms, and its value is 4/5. So it's convergent. And that's it. That's the last example in 11.2.